Hi, this is going to be for Chem 102. We're going to talk about section 14.6, which is all based on this equation called the Arrhenius equation. The Arrhenius equation has a couple of pieces. Um, got your K, which is your rate constant. Then we have this letter A, which is called the collision frequency. We call it the frequency factor, but it represents how frequently do we have effective collisions. You would either be solving for it or you would be given that number. And then we have EA, which is the activation energy in kilojoules per mole. So you would need to make this in joules per mole. Usually it's given in kilojoules per mole, but we're using R, the gas constant with the joules, not the liters and atmospheres, because we're dealing with energy here. So we need the gas constant for energy. And notice that the units would have to match. Then T would be the temperature in Kelvin. Again, the units would have to match. And then E is just the base of the natural log, right? So if we wanted to get rid of E, we take the natural log of both sides. If we want to get rid of natural log, we raise everybody to the E. So I don't know what happened in this slide. I tried to find the original, none of my PDFs are showing actually what I can guess of what they are meaning. They take the natural log. You take the natural log of both of these sides, right? So we do ln of k is equal to ln of a e to the negative ea over rt. That gets rid of the e. That brings all of this down. But essentially what you don't need to know the derivation. You need to know this equation. And if we look at this equation, you may see how we might be able to use it experimentally. Do you see it? Y equals mx plus b. So we really love this getting the linear equation because we can find our slope, and because R is a constant, our slope can give us the activation energy. So it may be hard to measure activation energy, but we can measure rate constant doing different experimental things like we've talked about. We can measure temperature, and then we can measure or look up the frequency factor, the collision frequency factor. So why don't you take this equation and think about how we could plot um, the natural log of k versus 1 over t, right? Because if my y is natural log of k, my x would be 1 over t, just like a Clausius-Clapeyron equation, essentially. Right? The natural log was the pressure, and then 1 over t was our x. So why don't you just take a moment, maybe go into Excel, get those Excel skills, and plot this, and see what you get. So if we plot this, we would first have a chart in Excel that would have the natural log. So I would just type into Excel my k and my t's, and then I would type another cell that would be ln of k, and I would just say equals ln of whatever that cell was, and then I would drag it down. I can show you some of these tricks in class if you want, but getting good at Excel is really a life skill, and so definitely worth your time. And then my next column would be 1 over t, and in this column I would say 1 over, and then I would put in that cell and I would drag it down. So we get these numbers, and then we would plot a graph of these two numbers. And so we get this graph. Now, if we wanted to find the slope, remember that the slope would give me negative EA over R. So if I find the slope, I can find the activation energy. To find the slope, we would just pick 2 points and we do rise over run. Or if we have Excel, we just plot a trend line and we look at our trend line equation to find our slope. So either way, if we pick the 2 points, then you can also pick 2 points from the graph here. So if you just pick like this point, you can do these would be your x values and these are going to be your y values. So you would do change in your ln of k's over change in your 1 over t's. And then you could plot your slope just from the actual table. or you can plot from a graph either way. But I think that you should be prepared on a test to be given a graph like this with values that you can kind of see and then be able to plot or tell slope from those graphs. So if you wanted to try to make your trend line and stuff, you should be seeing that your slope is negative 5.5 times 10 to the 3. And then that would mean that our activation energy would be the negative slope times R, plug in our slope, plug in R, and you get out 4.6 times 10 to the 4 joules. And if we turn that to kilojoules to make it a little easier to read, it's 46. K has units of inverse molarity inverse seconds, but ln of K has no units. And then, of course, like Clausius-Clapeyron, we can also have a two-point form of the Arrhenius equation. So you're not going to be given this, but we can relate it to Clausius-Clapeyron. So if Clausius-Clapeyron is P1 over P2, then Arrhenius equation is K1 over K2. Clausius-Clapeyron is delta H over R, but Arrhenius is activation energy over R. Clausius-Clapeyron is 1 over T2 minus 1 over T1. And Arrhenius equation is also 1 over T2 minus 1 over T1. So things we're changing from the Clausius-Clapeyron are going to be our P's turn into K's, and our delta H turns into activation energy. Why don't you try using this? The first order reaction here, I'm giving you the temperature, I'm giving you the K's. Can you get the activation energy using the formula? So to use the formula, I'm just going to solve for EA. Now, I'll show you in class, but there are easy ways for you to break this up. You could make K1, K2. We can just say, hey, let's just call this X, and we can take this T1 over T1, T2 minus 1 over T1, make that Y, and then it becomes a lot easier to navigate. So if I have ln of X is equal to EA over R times Y, it's a lot easier to solve for EA. Right? So EA would be R times the ln of X over Y. And then you can plug in X is equal to K1 over K2 and Y is equal to 1 over T2 minus 1 over T1. And I think that's just an easy way to rearrange things without getting too bogged down in the K's and the T's. So if you haven't tried it yet, try it now, maybe with that rearrangement and plug in your numbers. You should get 91,000 joules per mole or 91 kilojoules per mole. So in this one, oh, and I forgot to, so for this one, first order reaction has activation energy of 83 kilojoules per mole. Rate constant for the reaction is given here at this temperature. What's the rate constant at this temperature? So we're solving for one of the K's. So pause and try this out. Okay. So they rearranged it again. If you are like, hey, I can't rearrange it, I gotta plug in numbers, plug in numbers. Again, you could use X's and Y's. And so what I would probably do is I would just solve. So if I had ln, let's say X is equal to EA over R times Y. What I'm trying to solve for is X. Remember, X is gonna be K, what do we call? K1 over K2. There's many different versions of this online, so be careful. So X is K1 over K2. If I can solve for X, then I can plug in K1 and get K2, right? And so if I want to solve for X, we would take the natural log of both sides. So X would be equal to E raised to the EA times Y over R. And then if I know what my EA is, I know what my R is, I can actually figure out what my Y is. So we can actually plug in numbers and get a number for Y and plug that in, and then we can solve for X. And so that's kind of what they're doing. And then once we have our X, remember X is equal to K1 over K2, and then we could just solve for K2 would be equal to K1 over X, whatever your X was. I know that seems a little complicated, but just try it out however you want. If you want to plug numbers in and then rearrange them, if you want to try to rearrange and then plug numbers in, there are easier ways to do it than just grappling with all the K's and the T's. So your answer for this one, rate constant at 300 should be 10 inverse seconds, or 1 times 10 to the 1 inverse seconds. And if it's 2 sig figs, it should have a decimal there. And then that's all going to be all for this video. We're going to do some more math practice in class.